Pascal's triangle is a fun way to organize binomial coefficients. So the way that it works is that you make a triangle out of the binomial coefficients. Now, of course, you can continue here. So you put 0, choose 0, 1, choose 0, 2, choose 0, 3, choose 0, and so on. And then to the right, you increase the choose part. So to the right of the 1, choose 0, you get a 1, choose 1, and so on. And you write it in this triangular form. And many of the things we saw about binomial coefficients will translate to interesting properties of this triangle here. So for example, we saw the Pascal's identity. And so what did Pascal identity say? It said that n choose k is equal to n minus 1 k minus 1 plus n minus 1 k. And what this means is, for example, so let's say you want to compute 5 choose 2. So 5 choose 2 will be the sum of 4 choose 1 plus 4 choose 2. And what this means in the drawing here is that this 5 choose 2 here is the sum of 4 choose 1 plus 4 choose 2. So this is the sum of these two. And if you replace for all of them, you'll see that it's always the case that an entry here is the sum of the two above them. And so, of course, all of these on the left here and on the right are equal to 1, because 0 choose, like the amount of ways that you can choose 0 is equal to 1, and the amount of ways that you can choose the whole set, so 4, how many ways can you choose 4 is equal to 1. And so with that, you get a nice little pattern here. Let me write it with a different color. So 1, 1, 1, 1, 1. And for the 2 choose 1, it's the sum of these two. And so this gives you a 2 here. Now here it's a 1. Then the sum of 1 and 2 is 3. 1 and 2 is 3. And then you get a 1 here. Then there's another 1. And the sum of 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. And you get another 1 here. And for the last row, so this will be 5. This will be 10, 10, 5, and 1. And so notice that this gives us a nice way of finding these values sort of recursively with the triangle. So what is 5 choose 3? It's going to be equal to 10. And you can find it by, so 5 choose 3 is going to be the sum of this one and this one, but this one is the sum of this and this. This one is the sum of this and this. So you need to find these three. This one will be the sum of this, and so on. And so there's a nice structure here on how this triangle is built. The other thing that's interesting here is we saw, so if you look at the rows here, we saw that when you sum up these rows, remember the sum of the n choose k was 2 to the power of n. So if you sum up the rows, let me write those sums here. So for the first row, you get a sum of 1, which is 2 to the power of 0, right? So let's write it like this. So 2 to the power of 0 equal to 1. For the second row, you get 2 to the power of 1, which is equal to 2. So 1 plus 1 is 2. Now 1 plus 2 plus 1 is going to be 4, which is 2 squared. 1 plus 3 plus 3 plus 1, so 3 plus 3, 6, 7, 8 will be 8, which is 2 cubed. Then here it will be 1 plus 4 plus 6 plus 4 plus 1, so 6 plus 4 is 10, 14, 15, 16. So that will be 2 to the power of 4 equal to 16. And this one will be 10 plus, so 1 plus 5 plus 10 plus 10 plus 5 plus 1. 5 and 5 is 10, you get 32. So 2 to the 5 equal to 32, and you can continue like that. So the sums of the rows of the Pascal triangle give you powers of 2. Also, we have that these are the coefficients in the expansion. Remember the binomial theorem. So let me write this in a different way here. So again, if you want to do what we did for 5, let's do for 4 here. So if you do x plus y to the power of 4, you just need to look at this row here. And so this will be equal to x to the power of 4 plus 4 plus 4 times x cubed y plus 6 x squared y squared plus 4 x y cubed plus y to the power of 4. So if you want to know how you can expand these x plus y to the power of n, you can just read the coefficients out from this row. We also saw that, again, you had this symmetry here that came from the fact that the ways that you can choose from 5 choosing 2 is the same as from 5 choosing 3, because when you choose 2, you also, so if you choose 2 elements, it's the same as choosing which ones you don't choose. So in other words, it's just that n, write it here, that n choose k is equal to n choose n minus k. So in how many ways can you choose k elements? It's the same as choosing the ones that you won't choose, the n minus k that you won't choose. And this converts into, so this here essentially is a symmetry, saying that there's a symmetry here on, it's like a mirror here from right to left, right? So you get the 3 and the 3, the 4 and the 4, the 10 and the 10, the 5 and the 5. So you actually only need half of the triangle because the other one is just a copy of it. So yeah, so Pascal's triangle has, and there are many, many more properties. Many of the properties of binomial coefficients, they essentially translate to some nice property in this triangle.